Imagine building a spam filter that seems to work perfectly. You collect thousands of emails. You train a naive Bayes classifier. You calculate all the probabilities. And everything looks great. Then one day, it completely breaks. And the reason why reveals one of the most important lessons in machine learning. Let's start with the problem. Naive Bayes treats an email as a collection of words. For every word, it learns how likely that word is to appear in spam emails and normal emails. Then it combines those probabilities to decide whether a new email is spam. Simple, fast, elegant. But there's a hidden problem. Suppose you've never seen the word nips before. According to the standard naive Bayes formula, its probability becomes 0. And because naive Bayes multiplies probabilities together, 1 0 destroys the entire calculation. The model isn't saying the word is unlikely. It's saying it's impossible. So how do we fix it? This is where Laplace smoothing enters the story. Instead of assuming unseen events have 0 probability, we pretend we've seen every possible outcome at least once. To understand why, imagine a football team that has lost all 4 away games. Raw statistics say their chance of winning the next one is 0%. But 4 losses don't prove they'll never win. So Laplace smoothing adds 1 imaginary win and 1 imaginary loss. The estimate becomes much more reasonable. The exact same idea fixes naive Bayes. Every word gets a small count added to it. Now unseen words no longer have 0 probability. The model becomes far more stable. But researchers noticed another limitation. The version of naive Bayes we've been using only records whether a word appears, not how many times it appears. Imagine an email that says, drugs. Buy drugs now. The word drugs appears twice. But the model treats it exactly the same as if it appeared once. Important information is being thrown away. So researchers developed the Multinomial Event Model. Instead of recording whether a word exists, it models the actual words appearing throughout the email. For text classification, it often performs much better because it preserves word frequencies. But here's something fascinating. Even after all these improvements, naive Bayes usually isn't the most accurate classifier. Algorithms like logistic regression often perform better. So why do people still use naive Bayes? Because it's fast. Training mostly comes down to counting. No expensive optimization. No gradient descent. When starting a machine learning project, don't begin with the most complicated algorithm. Start simple. Build something quickly. Test it. Learn from its mistakes. Then improve it. Machine learning works the same way. A simple model that reveals the real problems is often more valuable than a complicated model you don't fully understand. And that brings us to the next chapter of the story. So far, we've looked at logistic regression, Gaussian discriminant analysis, and naive Bayes. But they all leave us with one question. If our goal is classification, how do we find the best possible decision boundary? Not just one that separates the classes, but one with the largest possible margin? Imagine drawing 2 lines that both separate the data. One passes dangerously close to the examples. The other leaves a wide safety gap. Intuitively, the second boundary feels more confident, more robust. That simple idea became the foundation of one of the most influential machine learning algorithms ever created: support vector machines. But a challenge still remained. What happens when the data can't be separated by a simple line? One approach is to manually create new features: squares, cubes, interactions between variables. But what if we could automatically work in thousands, or even infinitely many features without explicitly creating them? That idea became one of the most powerful concepts in machine learning: kernels. And that's exactly what we'll explore in the next video.